After reading this module, you shall be able to know the importance of correlation diagrams. Also, you will learn the various characteristics of the correlation diagram, as well as you will be able to identify various irreducible representations originating from weak and strong field of the ligands involved. For interpretation of the electronic spectra of metal complexes, it is important to understand the origin and type of occurring transitions. To understand possible transitions involved and their related energies, we have to know the various parameters such as ligand field splitting energy and electronic configurational effect on this very energy. For this purpose, special emphasis has been given to the correlation diagrams, which themselves are self-explanatory in terms of various visible transitions. The diagram makes use of the free ion terms which are at hand without the presence of weak as well as strong field ligands in the extreme end.
Let us discuss the splitting of a system with dn configuration. In a free metal ion, the 5d orbitals, namely dxy, dxz, dyz, dx square y square and dz square are degenerate in nature. When we apply a spherically symmetric field, the energy of d orbitals is raised up due to the electronic repulsions, but it still remains degenerate. But if the applied ligand field is not spherically symmetric in nature, the degeneracy of the 5d orbitals is lifted, giving rise to the splitting of orbital energy levels. This happens due to different orientation of the 5d orbitals with respect to the approach of the ligand axis. Here we will talk only about the most common type of the geometry observed in coordination complexes, which is octahedral, comprising of the 6 ligands approaching the metal ion along the 3 coordinate axes along the positive and negative directions. The splitting of orbitals is represented according to which it can be seen that the orbitals dxy, dxz and dyz are lowered in energy and dx square y square and dz square are raised in terms of energy. The splitting of the d orbitals in an octahedral ligand field. On the extreme left, it is shown a metal ion Mn plus and the 6 ligands L at the infinite distance away. If the electrostatic field created by the point charge ligands is spherical, the energies of the electron in the 3d orbitals are raised uniformly, as is depicted in the center. On the extreme right is the case when the electrostatic field created by the point charge ligand is octahedral. The energy of the electrons in the 3d orbitals that point directly at the ligands is raised with respect to that in the spherical field, while the energy of the electrons in the orbitals that point between the ligands is lowered with respect to the spherical field. The changes in the energies of the electrons occupying the d orbitals of an Mn plus ion when the latter is in the octahedral crystal field. Here, the energy changes are shown in terms of orbital energies. Next, we are going to discuss the free ion terms and how their splitting takes place. The free ion terms are atomic states which are characterized by the values of total orbital angular momentum represented by capital L, total spin angular momentum represented by capital S, and total angular momentum, which is calculated using the coupling of the spin and orbital motion represented by capital J. Interpretation of these terms is very important in order to understand the electronic spectra of the coordination complexes. The word term symbol is a special name given to these free ion atomic states which describe individual atoms or the ions in the absence of any Ligand field. The term symbol is represented as 2s plus 1 capital L, and in the subscript we have J. Electronic configuration is split into terms due to inter-electronic repulsions, which is split into states by spin-orbit coupling, which is further split into microstates by the magnetic field. The above sequence is represented in the form of a diagram where we can see the splitting of the electronic configuration in terms due to electronic repulsion, which further gets split up into states due to spin-orbit coupling, which further splits up into microstates using the help of magnetic field. The sequence shows the splitting of the free ion terms due to spin-orbit coupling and inter-electronic repulsion parameters. For a particular system, the spin multiplicity is assigned according to the number of unpaired electrons. In case, for example, if we talk about a D2 configurational system, the number of unpaired electrons is 2, so the spin multiplicity is either 1 or 3, depending on whether the electrons are paired or unpaired. Splitting of the free ion terms. Free ion terms originate when the metal atom or ion is free from any surrounding Ligand environment. But in actual practice, this is not the case when we are talking about a metal complex. The ligands surrounding metal center will always influence free ion terms according to their geometry. Just like the splitting of d orbitals in the presence of ligand field, the splitting of free ion terms will also take place in the presence of the surrounding ligand field. The ligand field can either be weak or strong, but in actual practice, the case is always somewhat between the two extremes. Thus, we have to find the splitting of free ion terms for strong as well as weak field cases. In the case of weak field splitting, in the presence of weak field ligands, spectroscopic terms arouse from the free ion terms. Because of the weak field, the overlap of the orbitals between the metal and ligands is not very good, and thus we can say that geometry of the metal orbitals is not disturbed to a large extent. Because of this, the metal ion retains its identity to some extent and give spectroscopic terms which are transformed into group theoretical terms. This has been represented, which shows the splitting of free ion terms in octahedral geometry. It can be seen that the S term in the case of group theoretical terms in an octahedral environment splits up into A1G. The P term splits into T1G. The D term is splitted up into T2G plus EG. The F term splits up into A2G, T1G and T2G. The G term splits up into A1G, EG, T1G and T2G. The H term splits up into EG, T1G, T2G, and T1G. In case of strong field splitting, when the ligands start approaching the metal ion which is strong, interaction between the metal center and the ligand orbitals is enhanced and it increases the ligand field splitting parameter and the extent of splitting. In this case, the metal orbitals subside from their original geometry and symmetry, and hence the spectroscopic terms are no longer obtained, but we can only have group theoretical terms for various possible configurations. The group theoretical terms are obtained by using the direct product of the occupied orbitals. As an example, we will be taking D2 configuration, which can have following possible orientations in an octahedral field. This strong field approach is very useful in assigning the order of energy to each group theoretical term. Table 2 shows the origin of group theoretical terms in an octahedral geometry. In case of having a T2G2 configuration, it will be ground state with the direct product of T2 into T2, which will be equal to group theoretical terms of A1G, EG, T1G, and T2G. If we have the first excited state T2G1, EG1, the direct product will give the group theoretical term as T1G plus T2G. In case of second excited state of T2G 0 EG2, the direct product is going to give the group theoretical term A1G, A2G, and EG. Next, we are going to discuss the correlation diagrams. In order to draw the correlation diagrams, the following steps have to be followed. First, on the extreme left, free ion terms are given in order of their increasing energies. These states have actually arisen from the spin-orbit coupling and electronic interaction of the electrons as per their electronic configuration in a particular system. The symmetry characteristics of these free ion terms will eventually lead them to their breakdown into irreducible representations in an octahedral field. This is again represented at the left side along with the free ion terms. This represents the weak field case where the ligand field is not strong enough to alter the spectroscopic terms to a large extent. Extremely strong field case is represented at the right end of the diagram where group theoretical terms are represented along with the electronic configurations in their order of energy. Each free ion irreducible representation is then matched with the group theoretical states of the strong field with the same symmetry and multiplicity. To emphasize the fact that transitions to the excited states having same spin multiplicity as the ground state are more feasible, the line joining ground state with excited states of the same spin multiplicity are shown with the darker lines. A non-crossing rule is also observed according to which the lines connecting the states of same symmetry designation do not cross. The splitting of weak and strong field in their respective group theoretical terms on the extreme left is shown free ion terms. To its right is shown weak field terms. To its further right is shown strong field terms, and on the extreme right is shown the strong field configurations. The correlation diagram for a D2 configuration in octahedral geometry. On the extreme left is shown the free ion terms which are splitted by the interaction of weak field into the spectroscopic terms, and on the right is shown the strong interaction which leads to the splitting of free ion terms in group theoretical states. On the extreme right, it can be shown that on the ground state we have T2G2, which is splitted up into triplet T1G, 1 T2G, 1 EG, 1 A1G. The first excited state is T2G1 EG1, which is further splitted up into group theoretical states as triplet T2G, triplet T1G, 1 T2G, 1 T1G. The second excited state is EG2, which is splitted up into group theoretical states as triplet A2G, 1 EG, 1 A1G. The states on the left and the states on the right have to be connected by a line maintaining a non-crossing rule.
To understand the possible transitions and their related energy, we have to understand the various parameters such as ligand field splitting energy and electronic configurational effect on this energy. Correlation diagrams are self-explanatory in terms of various feasible transitions. The diagram makes use of the free ion terms which are at hand without presence of ligand field and weak as well as strong ligand field in the extreme end. Non-spherically symmetric ligand field lifts the degeneracy of 5d orbitals, giving rise to the splitting of the d orbitals. This happens due to different orientations of the 5d orbitals with respect to the direction of approach of the ligand axis. Free ion terms are atomic states which are characterized by values of the total orbital angular momentum represented by L, total spin angular momentum represented by S, and total angular momentum which can be calculated using the coupling phenomena of the spin and orbital motion. The word term symbol is a special name given to these free ion atomic states which describe the individual atoms or ions in the absence of any ligand field. The ligand field can be either weak or strong, but in actual practice the case is always somewhat between these two extremes. Thus, we have to find the splitting of free ion terms under strong as well as weak field. Due to weak field, the overlap of the orbitals between the metal and the ligands is not very good, and thus we can say that geometry of the metal orbitals is not disturbed to a large extent. Because of this, the metal ion somewhat retains its identity to give spectroscopic terms which are then transformed into group theoretical terms. When ligands approaching the metal ion are very strong, interaction between the metal center and ligand orbitals is enhanced and the metal orbitals subside from their original geometry and symmetry. Thus, the spectroscopic terms are no longer obtained, but we can only have group theoretical terms for various configurations possible. Correlation diagrams are drawn with left side occupied with free ion terms and their irreducible representations, and on the right hand side are drawn strong field configurations with their respective group theoretical terms. Both the states on the left and the right are joined having the same symmetry.